There we go.
This meeting is being recorded.
Fantastic.
Go ahead.
All right. So thank you very much for everyone for coming today. Today we have the pleasure to have Dr. Bhatia Koswari, Ravi for as our instructor today on visual data, specifically on more or less on OpenCV in Python. So I'll just briefly introduce Bhatia a little bit. So Bhatia is a medical doctor with 2 masters in medical education, MHPE, and public health, MPH, from the Tehran University of Medical Sciences. He has been a full stack developer as well since he was 19. Since the pandemic, he started focusing his research on deep learning as a way of helping those suffering from the disease through early diagnosis and efficient triage. He has started his research at Radiology Informatics Lab at the Mayo Clinic in 2021 and has been working on complications risk predictions in orthopedic patients and several generative tasks. Bhatia has shared with me the GitHub repository of today's session, which I will drop in the chat right now, and you can go ahead.
Okay. Good morning, everyone, or good afternoon, I guess, there. So it's a pleasure being with you today. Today we'll be talking about visual data processing with focusing on 3 libraries, starting from very simple ones like Pillow, and then SkyImage, and then going to the advanced one, which is OpenCV. Today, I hope we can have an interactive class. So whenever you have any questions, feel free to interrupt me. I hope I can answer all your questions, but if there are some things left at the end, we can talk it after the class or via email. Also, there are 3 code challenges here in this notebook. And at each time point, we'll go through them. There are 2 of them are one-liners and 1 to 2-liners, and the last one is 6 or 7 lines. So depending on your understanding from Python, you will be able to complete them very easily or with a little bit of work, but we'll be here to talk through how to pre-process images using Python. So first of all, let me share my screen and then. Okay, can you see my screen now?
Yes, I see my own face.
Okay, perfect.
Yeah.
So first of all, let's go to the Colab website, which is colab.research.google.com. So let's all go from here. And then you will probably see this pop up, or if you don't see that, you can click on File, Open Notebook, and then go to the GitHub. It will ask you to authorize. You don't need to do that, so don't worry about that. Just uncheck this, include private repos, and paste this link, and I think it should be in the chat also. Yes, thank you so much. And you will see this tutorial.ipymb, and you click on this arrow. This will be our notebook for today. Okay, so this workshop will be divided in 3 main parts. So the first part is just data preparation. You don't need to worry about that. The first part is introduction. So how images are encoded and why do we see them as we do in Python or on our monitors. The next part will focus on the 3 libraries, as we mentioned. So we'll have Pillow, then SkyImage, and then OpenCV. And then finally, we'll have the final challenge, which is a 7-liner code. During this, I try to put everything in a notebook, but there might be some things that I say. So if you don't understand one part, just as I said, feel free to interrupt me. Let me just have this minimized there so I can see your faces too. Sorry. Here it is. Okay. Okay. So first of all, run this first cell to clone the data that we want from the repository.
Sorry,
And it says to,
Bardia, sorry to interrupt. Would it be possible to make the font a little bit bigger? If you can like zoom in
yes.
more. Yeah, it's a little bit.
How about now?
Yeah, it's perfect. Thank you.
Okay, of course. So go ahead and run this cell. I already cloned the repo and have the files here. That's why I get this error, but you shouldn't get that. And when you click on this file icon, you should see these folders. So the new samples, the samples, and some CSV file, MP4 file, etc. Oh, you don't need those. Okay. Any questions or any problems with that?
No, I think
Okay.
we're good. If there's any
Oh.
questions, please go ahead and drop in the chat, and everyone, you can make a copy of this notebook and go along at the same time while Barty is explaining. Yeah, I think so far so good. Thank you.
Okay. Okay. So, how are images made? So first, if you run this cell, which is a form, you'll see something like this. Let me zoom out a little bit. So what this is, it's just a table. So if you have worked with Pandas, which is an image processing, a tabular data processing library in Python, this is a simple table. These are the columns and these are the rows. What this image represents, or this table represents, is a sample from the MNIST dataset. MNIST dataset is a very well-known dataset of handwritten digits, created, I think, in 1996 or 7, something like that, by Dr. Lacan. And this was essentially the first dataset that was used to train convolutional neural networks with all those hardwares back then. But these images are 28 by 28. That's why you see 0 from 27, which makes 28 columns, and 0 from 27, which makes 28 rows here. And each value in this table represents the pixel value that is stored in the image file. And as you see, there are different pixel values ranging from 0 to 250. I think 4 is the biggest one here. Yes. 255 is the biggest one here. So this is essentially the color, the background color of each cell represents the pixel intensity. And so when you are opening an image in your computer or in your mobile phones, this is essentially what's happening. Each pixel value is represented by a number from usually 0 to 255. And then the intensity is different between based on that number. So this table background, the background color of each cell of this table is essentially showing that. So you can open the file and see that the file that's there is only made up of these numbers. I don't know if you can open up here. Yes, so this is what we have. And you can just scroll, but that's the table. And this is how images are shown, and this is how images are stored. After that, you see that each image will have a height, sorry, here, and a width. For example, for this image, that will be 28 by 28. And then the color images have a third dimension called the channel dimension. And when we want to represent that, we say H colon W colon C, which is the order that these numbers appear. So that will be H would be height, W would be width, and C would be channels. As I said, most of the images that we see are colored, and these colors are represented by 3 different channels that are red, green, and blue. So when you have a single image, you have 3 different channels, and essentially each pixel in your monitor has 3 different, let's say, yeah, they can show 3 different shades of these colors. So one would be red, one would be green, and one would be blue. That's how we represent these images. So this is very important. This H:W:C is very important. As you go into the deep learning world, or even in the libraries that we're going to discuss next, these orders will change. So for example, if you want to work with PyTorch, they say it's channel first. So this would be CHW. Or if you work with TensorFlow, that would be channel last. So that would be like this, HWC. So this is very important and it's something you have to pay attention to. So when we say an image, so for example, the image of this cat is 512 by 512 by 3, which means it's a colored image, probably. And then the height and the width would be 512. And so this is the convention. We can change the color space, for example, to HSL or etc. But this is the most common color space that we use. And if you remember, I said that highest number here is 255, 0 to 255. So that would be 256 numbers in total. The point here is that each pixel, we call these images 8-bit images, which means that each pixel value is encoded by 8 bits. And 8 bits is 2 to the power, 2 to the power of 8 means 256. That's why we have 0 to 255 numbers ranging from this. And if you want to have higher dynamic range, then you have to create higher bitrate images. For example, in medical imaging, when you have a CT scan, they are usually 11 bits or 12 bits. We also have 16-bit images, which means that rather than having from 0 to 255, we can have 0 to 2 to the power of 16 minus 1 pixel values, unique pixel values. So that's the difference between them. I read a study. I wanted to put the citation here, but I just couldn't find it. But I think humans can only detect 30 shades of gray. So if we want to have 0 as black and 255 as the white, we can only discern 30 different shades here. And that's very interesting when you want to do medical image analysis. But the computers are not like us. So this, when you have, for example, when you convert a 16-bit image to 8-bit image, you might not understand the difference or you might not see the difference, but finally the computer will see that. So if you can, use the higher bit images so you can store more information. Okay, so this is the introduction part, and that's how 8-bit images are created. Next, let's go to the libraries that we want to talk about. So a disclaimer here that most of the images that we'll work with in this session are created by Stable Diffusion. I don't know where the other reference go. I can put it here. I will update this one. There's another reference where I took the images from. But essentially, Stable Diffusion is a deep learning based model that can create images from text prompts. So let's see. Let's make it a little bit more interesting. I don't know if we can see it here or not. Oh, I should have access to that. Okay, we can wait a little bit until this one loads. Okay, I'll open this in a moment. I think we can have Dolly here. Okay, that's great. So these images, these models, which are called diffusion models, create images from a text prompt. So let's see here. Just trying to find the demo. No, not here. Okay. So for example, here you see that this image was created by this prompt. So a 3D render of a tropical fish in an aquarium on a dark blue background digital art. So this is what the model creates. So these images are all synthetic. And So I'm using the same concept here for the images that we'll discuss in this session. So today we'll be discussing 3 different libraries, Pillow or PIL, SkyImage, and OpenCV or CV2. We will, all of them have their own pros and cons, and for specific tasks, you might like to use one of them over the others. I will try to discuss why we need, for example, how I use each of them during our research workflow, but feel free to ask any questions or provide your context so we can help with uh, um, let's say understanding which one is suitable for your work right now. So Pillow is a fork of Pill. It's based on C. So as you know, Python is a very good programming language. It's very easy to understand, easy to read, pretty easy to debug. But the problem is it's super slow. So it's 70 times slower than C. Yes. And that's very slow. So if you want to do something really fast, you have to do it in C. And there are many, many libraries out there that are just a Python wrapper around the original C program, or just call the binary, which is in C format. So PIL is one of them. Also OpenCV that we'll discuss later is another one. So these libraries are very fast. So if you want to do something you want to highly optimize your workflow, then these 2 libraries are the go-to ones. But these create some issues, as we will see. So Pill or Pillow comes with, I think, every standard Python installation. So if you just have Python installed, a minimum Python version installed, this should be there. But if not, you can use this command to install all the 3 libraries that we will be discussing today. So this will be Pill. So from now on, we'll call it Pill. And from Pill, we import the image module, which takes care of image opening, closing, and also image transformations that we'll discuss. So if we run this cell, this is the first image that we have. In this samples folder, we'll have 14 images in PNG and JPEG formats with different characteristics. And at the end, the whole goal of this session is to write a function in whatever package that you're more comfortable with, or even mix them to make them all the same, look the same. And we'll discuss that. But for now, this is the first image. As you see, I didn't do anything. So I just called open. And then after that, I just used just copy and paste the variable name. And you see that the image is shown. So the first thing is most Python interpreters, especially Jupyter Notebook, Jupyter Lab, Colab, VS Code, etc., they have built-in functionality to open PIL images. So you don't have to use other external libraries like Matplotlib or the built-in functions of the other libraries to show an image. So this is very, very useful if you just want to inspect one of your training samples in a training set, or you want to see if there is an image, if it looks right, looks wrong, or if you're doing something that you're creating an image and you want to inspect that on the fly. So this is a very good one. This is a very good perk of this library. And then we can, as you saw, images are just matrices. So we can convert an image to a NumPy array and then see that. So here you can see that the shape of the image is 667 by 1000 by 3. So as we said, this is the height of the image, this is the width of the image, and 3 is the number of channels. So you can see that this is 667, this is 1000, and we have 3 channels in the channel dimension. And then this is something very interesting that you have to pay attention to. The image type, which is the NumPy array D type, is uint8. And what it means is that uint means unsigned. So you will have as we talked, these are 8-bit images. So the 8 is from the 8-bit. The int means they are integers, so we won't be dealing with floating points. And finally, the U is unsigned. So it means that the numbers here are can range from 0 to 255. That's what a uint8 means. So if you want to open images with PIL, you have to make sure that the D type is uint8, or I think there's a uint8, uint16 also mode there, but this is it. So you can't open floating points images directly with PIL. You have to convert it to either of these two formats. So this is the first difference. And let's open that. Let's show different individual channels of this image using Matplotlib and NumPy. So as you said, this image has 3 channels. Using NumPy, we can get here. The first axis would be the first channel. The second one would be the second channel, and the third one would be the third channel. And as you know, these arrays are 0 index, so this would be 1, 2, 3. And the colors are the color of the channel. And if we show that, these are the 3 individual channels that create this image. So if you look at this point, for example, or this big circle, you see that it's mostly red. And if we come up, yep, it's mostly red. That's just some way to say these channels represent which color. And there's less blue in it. So each image is created by 3 different channels. Okay, so far you might ask yourself, so how did we have a grayscale image with 1 channels? So what's the relationship between grayscale images and the channel dimension? Anyone? You can type it in the chat if you like. Okay, grayscale is 1D. So what do you mean by 1D? Is the channel red or green or blue? Okay, the 1 channel dimension is how dark that pixel is. That's correct. As we will discuss later, grayscale images can have 1 channel or 0 channel. So if you understand the concept of channel or dimensions in NumPy, it means just adding 1 more dimension. If we have only 1 channel, we can remove that dimension. That's why we can have 0 channel images. When we say that an image is 1 channel or 0 channel, essentially it means that all the values here show how dark, or to be more correct, how bright a pixel value should be. So 0 is very dark or black, and 255 is white. One thing to mention here is that, as I said, these monitors, all the monitors that we're looking at right now, have 3 main colors of red, green, and blue. And every color that we see should be a mixture of these 3 channels. Exactly. So when we have a grayscale image, essentially what it means is that we have equal values of red, green, and blue in that specific pixel. So when we say 198, so it means that we have 198 out of 255 red, the same amount blue, and the same amount green. So this is what a grayscale image represents. So we can convert everything to grayscale. So you can make this image grayscale, but just copying, you can make this image grayscale by, let's say, getting a mean value of each pixel from red, green, and blue, and then replicate that 3 times for each channel. So that will be that would be a grayscale image. Note the difference between grayscale and black and white, or sometimes they say or binary images. So binary images, as the name represents, is just 0s and 1s. So we'll discuss that later during the tutorial, but that's essentially the difference there. Okay, so these are the 3 channels. And if you want to make this image grayscale, then I think I saved that here. We can take the mean across the second axis, which is the last axis, which is the channel 1, And then we can have, let's say, image, which was imported from Pillow, from array, which means that we are giving it a NumPy array. And note that we have to convert it to uint8 because these might create, when you take the mean of 3 numbers, there might be floating points there. And when showing that, we will be having this grayscale image. Yes. So this image is the grayscale version of this one. Any questions so far? Okay. The next part is some transpositions or transforms. For example, here you can just say, rotate this image by 90 degrees. And note that you have to pass something like a flag there. These are all C-based. So you can't say, okay, rotate this image by, let's say 95 degrees or 45 degrees. So you can only pass here 90 to 70, 180, and 360 would be essentially the same. So we don't have that. So that will be 3 rotation ones. And then you can also flip your images. When you want to train a deep learning model, there's a phenomenon that happens, which is called overfitting, which means that your model is will be very good at memorizing essentially your training set and will not will not learn the features that will help it generalize over the validation set. So we do a technique called augmentation or data augmentation, which we create copies with different looks of the training data to make this phenomenon happen later. I don't say it won't happen. Depending on network, it will happen sooner or later. But when you do augmentations, you're essentially having images that are different from this because computers don't have an understanding of how this image looked like. So if I give you this image and give you this image, you can probably take a look at it and say, okay, probably these two, there's a flip here happening here, and also the color is changing, but that will be it. But computers looking at different individual pixels won't have this overall understanding of the image. So by changing this simple rotation, a simple flipping, etc., you can see that you can fool the computer that this is a new sample. For example, looking at a cat that's facing to the right or facing to the left would be different for the computer. And that's where these augmentations, or let's say these transpositions, come to help you during your journey. So this is essentially what Pillow does. You can save the image finally, as we said here, and that's it. So when you want to do simple image inspection in your interactive environment like Colab or your notebook, definitely use Pill because it's first fast, and then there's a native functionality to open those and show those images. The other libraries that we're going to talk about open the images, but open them in a array format. And by array format, we mean that these images will be shown as a NumPy array, and we have to use Matplotlib or other libraries to play with them. So the next one, we go to the Sky image. This one is the most Pythonic image processing library out there. So if you're comfortable with Python, this is the library that you'll be most comfortable with. And you can call everything by a function. You can pass it numbers. You don't need flags. That will be very easy. But as we said, this is based on Python. Everything is written based on Python. So when you want to do heavy pre-processing on the images, or you have a multi-step pre-processing pipeline, then this will cause a bottleneck for you, and this will make it slow. But for routine training tasks, or even pre-processing tasks or post-processing tasks, this library is very good. For opening an image, you can use the IO module from the SK image. And if you run this, you'll see an array here. So you can see this is an array. Let's start from array. And then the data type is uint8, as we mentioned. And as I said, when we want to show the image, we should use imaging libraries like, plotting libraries like Matplotlib. This is the shape of the image as you see. So that will be 499 by 1000 by 4. So can anyone tell me what's this for? We talked about the RGB, that will be 3 channels. What's the fourth one? Great. Yes. So as you see here, this is a PNG image, and there is a plus side and a downside to using a PNG format. So PNG format by default doesn't have any compression. So that's a good thing. So if you save these images, the pixel values would be the same for you. And that's what we usually do when we have large training pipelines. As for example, we want to pre-process all our images and save them in a disk so that we can use them for a training task. We save them as PNG because it's lossless. But and it takes much more space. So this is another downside. The other thing is, as PNGs, as you've seen, has a transparency channel or alpha channel. This means that you can play with the transparency of each pixel individually, which is a good thing. But when you are trying to do image processing, or for most of the deep learning tasks, let's call it like this, for most of the deep learning tasks, you only need the 3 channels. So you can work with 4 channels, but 3 channels would completely answer your needs. So that's why some images that you open online, you find online, can have 4 channels. Sorry, and so the order of the channels would be RGBA, and the A would be the alpha, as I even said. I think if I mispronounce that, I'm sorry. So this is the 4th channel, and we have to get rid of this 4th channel if we want to have a 3-channel image. And with NumPy, you can do this. As these images are NumPy arrays, you can say the raw image would be a raw image and then index it. The first one is width, so we want all the width pixels. We want the height pixels. We want all the width pixels. And now we only want the first 3 channels. So that will be 0, 1, 2. And we're excluding the 3rd channel. So let's open this and let's print out the shape. This one is 499 by 1000 by 3. So we're getting rid of that last channel. Now, let's say we want to resize an image. We want to resize it to sorry, why do you say the 4th channel is the most important channel? Okay, so that's not a mistake, but that's how different perspectives work. So I've been doing a lot of design works in my school years, and PNG was always my go-to format because I could play with the transparency and save that as a transparent file. So for example, working with icons here, you want it to be this area to be transparent so that when you click on, there's not here. Yeah. So for example, when you click on that, then the background would not change, and you can change only the border cards, etc. The point is here that with deep learning tasks, you mostly care about the shape of the objects, not the transparency. I don't say it will be useless, but when you want to have a mix of images and train your model on a mixture of images from different places, then you have to select the dimensions that are mostly common across your set. So most of the images, even we have PNG. So the first image, as we saw, was also, I think, a PNG file. And that one didn't have a fourth channel of alpha. So here we're settling on 3 channels to take care of the shape of the image. The alpha channel will not usually affect the shape. I know you can change the opacity, but most of the time we want only the shape in deep learning models. There are some generative tasks that use the fourth channel, the alpha channel, but that's not very common at all, honestly. So the 3 channel is always the go-to number of channels. For medical imaging, for example, we use 1 channel, or when we concatenate multiple sequences, 2 or more channels. As I said, as what I wanted to say as get rid of this is most of the transformations in uh, these libraries, the OpenCV, not Pale, but SkyImage also require you to have a 3-channel image. So by getting rid of that, you're essentially having making your image compatible with these libraries, which will help you greatly in your image processing pipeline. So I'll go and now read your messages. So shouldn't do. So for computers, transparency doesn't mean what we have. So these are all numbers to them. So they won't understand if this is transparency or another color. So suppose that I create a monitor that has 4 channel, 4 pixel intent, 4 pixel, let's say, what's the name? Electrodes, or not electrode, but you can say uh, here, I can say I have a convention of having 4 channels, and that will be red, green, blue, that would be RGB, and yellow, for example. So that's why this number of channels is conventional based on monitor. RGB has been around, I think, since the beginning of monitor. So that's why stuck, and we have 3-channel images. But these are all numbers to the computer. So this computer doesn't understand what does the red mean. So that's why you can't say safely that computers don't understand transparency. They don't understand it as a context of transparency, but they understand it as a number. So whatever number you give to the model or to the computer, it will find a meaning for that in deep learning or machine learning. Okay, so if you want to say, if you have a grayscale image, you want to first convert it to 3 channels? That's a very good question. It depends on your task. So if you want to train, for example, your model on medical images that all have 1 channels or 0 channels, you have to make them all unified and look the same. So if you want to train your model with 1 channel images, you have to convert everything to 1 channel, as we did up here, the grayscale one, getting a mean across the channel dimension. But if you want to train your model on 3-channel images like RGB, so for example, you want to mix everything together. So you want your model to detect stable diffusion generated images from chest X-rays, from chest CTs, which the 2 latter might be grayscale and 1 channel. You want to convert everything to 3-channel. So having a compatibility across all your samples. In deep learning, we will do something called batching, which we will take care of. We will get into a little bit at the end of this session. But when we do batching, we want all our inputs to be the same size and same shape, and then put them together as batches so our processor can work on them faster. That's why we have to convert everything to a single standard. So for your model, it might be 3 channels. For my model, it might be 1 channel. But everything should be the same. Okay, any more questions? Okay, so okay, by stable diffusion images, I mean images that were generated by the computer here. So if you open the content folder here on the samples, you can see images 1 to 14. So image 1 to 13 are created by Stable Diffusion, which is something like the model I showed, the DALL-E 2 model that I showed earlier. But image 14, I guess, yes, this is a chest X-ray. I got that from the internet, so no patient privacy concerns here, but this is a chest X-ray. So for example, you want to train a model at the end that detects, that says this is a chest X-ray, or this is an image generated by Stable Diffusion, something like that. So, okay. So we want to resize our model, resize our image. If you remember, we said that for training deep learning models, we want our images to be the same size. So let's say I want to make this image half its size in each dimension. So I create a new image size, which is the raw image size shape. So let's take the raw image shape here. So that will be divided by 2, and the index one, which is the width, divided by 2. So you can see the order here is height and then width, which is what we showed at the in the initial example. And then we call resize, which is imported from the transform module of this sky image. And then we give it the raw image and the final size. This is very easy and very intuitive. And when we want to show that, and you see the number here, for example, was for 800. Now it's 400. And here it was 400, and now it's 200. So it means that the dimension of the image is changing. But let's say I want to change the width to 1/4. Now you see that the image is pushed, and let's say, yeah, you can see the aspect ratio. We call it aspect ratio, which means the ratio of width to height, or the height to width, sorry, depending on how you look at it. But this means that I'm changing the aspect ratio of the image. I'm shrinking the width twice as how I'm shrinking the width. So you can see the image is compressed. This is very important. So when you want to do deep learning tasks, then you need to have this aspect ratio as close to the original image as you had. So that's not a good thing. I have to put that to 2 if I want to, I want my model to understand the meaning of this image. And this is something cool happening when you use sky image that you have to be very, very careful about. And that is, my original image range was from 0 to 255, which was a uint8. But now when I did this transform, now everything is changing to 0 to 1. So essentially changing everything to floating point numbers from 0 to 1. This is very important. And when you want to save that, you should first convert it back to the 0 to 255 range and make it a uint. That's what is happening here. So if I want to save this image, I have to first multiply it by 255, which means I'm changing 0 to 1 range to 0 to 255 range, and then making that as a uint8. And then when I save that, that will be the resized image. So this is what I'm saving. So be careful about this data type conversion, as it will cause a lot of problems during your pipeline design. So about this. Now, let's say I want to crop my image. So we said that these images are all NumPy arrays. And when we say these are NumPy arrays, which means that we can do slicing on them. So for our first code challenge here, you'll have 2 minutes to write a function that will be a one-liner to center crop an image with a pixel size of with a dimension of 100. So suppose that I have this image, or this image that's 500 by 1000. And I want to get this center 100 by 100, something like that. I want to crop this image to be 100 by 100. So you don't send it in the chat until the 2 minutes is up. So that will be 12:50 for you. And then you can send your answers in the chat and then we can fill this up. But essentially that will be a one-liner. Also, let's add. Oh, 10:50, sorry. Yeah, that's not a problem. Farzan, I think that's a very big plus side for this model. As Ivan said, you have to fix the seed, which is written at the right side of the Dream Studio. But this is a very good thing. So for example, you can interpolate between different variations of an image and create a beautiful video, as we will see later in this course, but in this session. But yeah, so if you're not fixing the seed, you won't, chances are near zero to get two exact same images. Okay, so if you have written the code, you can share it in the chat, the one line. Okay. Okay, I'll go with Daniel's response, but I think Ivan's response is correct. Kai, I'll talk about yours. Andrew, I think yours was a little bit. So you have the size, so that's okay. We'll talk about this. Yours will give a little bit of different response. Resize we'll talk about, and then I think Anna's response was right, but that's fine. So let's copy and paste the code that I copied. So our image would be, we're not changing this. I just put original image here so we don't create any confusions, but we can just say image equals, there's one space here. So image equals image divided by 2, which we want. So here, what, I don't know, Andrew, yeah. What Andrew is doing is getting the center pixel of a single image. So whatever image I pass this, this one would be its center height, and the second one would be its center width. And then I want the middle 100 pixels, so based on size. So I will go 50 pixels to the left and then 50 pixels to the right. So that will be the middle 100 in terms of height, and then the middle 100 in terms of width. What I would change in your code is make use of this size argument. I know we say 100, that's totally fine, but when you want to write a function, you can put the size as an argument, so you can crop the middle 200 pixels or whatever. So let's say I'll put this divided by 2 plus divided by 2. And note that this 2 slashes means you'll get the integer part and you'll get rid of the floating points. So here, I think it was, yeah, Ivan, which you put int and then use 1 slash. It's totally fine, but if you can use 2 slashes, that will make your code much easier to understand and easier to debug later if you like. So I copy this, and then you put here this colon, which means the rest of the channels. Yes. And that's totally fine. You can put it, you can just remove that, because the rest of the dimensions of the image will be copied essentially if you don't put anything. So you can just remove that. And this is the middle part. So some of you said to use resize. So when I use resize, or if I use resize, so let's change this to 100 by 100. You see that the whole image is compressed and shrunken to fit the 100 and 100 part. We don't want that. We're changing the aspect ratio here, but here you can see this is just part of middle 100 pixel by 100 pixels square that is in the original image. So if I scroll up to the original image, that will be around this part. So others, I think one other person was have written something like this. So you get the center and then you go 100 pixels to the right, and then 100 pixels to the down in terms of, or down right. So that would be this. Now you see we're seeing something totally different, which is not a very good thing. So as we said, the middle 100, which means that you get the center point minus half that size and plus half that size in each dimension. So if you have, suppose in medical imaging, we work with 3D images like CT scans, which have 3 dimensions. So that's not channel. So we have a height, a width, and a Z dimension, and a channel dimension, which is usually 1, because they are grayscale. So by changing these dimensions, if you have this understanding of how this cropping work, then you can say, okay, now I can use this this knowledge to crop the middle cube of this CT scan or something like that. And if we change this and put this in the argument, then we can say, okay, now crop this image to be 200. Now you can see we have a bigger crop. So that's for the first coding challenge or practical challenge. Now, the second one is very similar to this. So suppose that we want to pad our images. So as you see here, when we do resize, we say that, okay, we have to give it this exact dimension, these dimension sizes, or the final dimension size that we want. And then if we say, okay, suppose that this image is, if you want to get the aspect ratio, that will be 2 to 1, which means 2 width and 1 height. Now I want to make that, suppose that's 500. So let's create an image that's 250 by, this one is 250 and this one is 125. I'll change this image. So you can see that the aspect ratio is pretty much the same. It's not changed. So just minus this 1 pixel that's divided by 4, which is, I think, negligible. So this is the image. But what I want to do is I want all my images to be squares, and I want all of them to be 250 by 250. What should I do? I should pad this. So when we do padding, we essentially add some 0 pixels to the dimension that's smaller to make it to the same size as the larger dimension, and essentially making a square. So depending on where you want to add this padding, you can have center pad, which means, for example, I have to pad this image by 125 more black pixels to the height dimension. So I can put that at the top, at the bottom, or make it half, and for example, have 62 at the top and 63 at the bottom, something like that. So this is what it means to do center padding. So now here, I want you to create this, to write this function or complete this function so that you can center pad an image with an arbitrary size. So here we say the margin of 100, and this 100 should be added to all the dimensions of the image. So to the top, to the bottom, to the right, to the left. And you'll have 2 minutes for this. And then after that, you can share your code here in the chat. So you'll need 2 lines of code. The first one, you have to create a large image that will be a placeholder for your smaller image, and fill that out with zeros, which means black, and then paste the image, the original image, in this area. Okay, you can share your codes. Anyone? Okay, so let's write it together. So first of all, we have to create, as we said, a larger image. And to create a larger image, we have to have the shape of the image and then add the paddings to the right, left, up, and down. So we say np.zeros, and then we should pass in a shape. For the shape, we'll have image, original image dot shape, index 0, and we want to add 2 times of the margin because we want to add it to the top and to the bottom. And we'll do the same for the other dimension. So that'll be it. And then the channel dimension is 3. So this is the size of our larger image. Now what we want to do is paste in the original image here. So let's see, a couple of people send their code. The large image equals, okay, the padded size is right, but you have to be careful about adding the channel dimension. So this is very important, because if you forget that, when you want to paste in your image, you'll get an error that there are different sizes there. So here you're essentially, okay. So the next one will be, now we want to paste in our image. So our image, or large image, now we want to index our code, index our array. So we want to say from our margin size to minus margin size, and from our margin size to minus margin size. And then the channels would be 3 equals image. So what we're doing essentially here is we're starting from the right, from the left, from 100 pixels, to go to the right to minus 100 pixels, which means 100 pixels to the left. And then here we're doing essentially the same for up and down, and we have the channels and paste it here. Any questions about this code? Let's see if it runs. I don't know if it runs, but it should theoretically run. But the image equals center pad image, and yolti.timeshow. The original one is raw image. Oh, sorry, that's supposed to be this. I'm changing the, so you see the margin is added. I don't know why this, the color space, the colors are changing a little bit. I had this issue last night also, so. Forgot to run this. Okay, so this is the issue. It says that the clip-in range, it should be between 0 to 1 for floats, or 0 to 255 for integers. So probably there's something changing here. So let's change that to, let's clip our image. I think we can have np.clip. 0 and 1. I don't know why are the pixel intensities are changing. I'll take a look at it during the class. So we'll have, I think, 20 minutes to cover a big chunk of the notebook. Not very big, but during this, I will try to debug this. There's something wrong happening somewhere in this code. So the other thing that we can do with SkyImage is transformations, which are much, much, much simpler than the other two libraries. So here, if we want to rotate this image by 45 degrees or 23 degrees, you can just pass in the number and it will take care of everything for you. And it will, you can see also the range is changing. So you have to be careful about this range. That's also between 0 and 1. And when you want to convert that or save that, you have to go back and change the, you can change it to 0 to 255. Sorry, I missed these two questions. Why pad based on margin instead of final size? That's totally true. I just wanted to show the overall approach of padding. At the end, the challenge, the final challenge focuses on exactly what you said. Guesstimating the aspect ratio. Okay. So that's what you're saying, Anna, is completely true, and you will experience that in the final challenge here. Okay, now OpenCV. OpenCV, as I said, is very good. It's based on C. It's super fast. It has lots and lots of capabilities. So whatever you think of, you just search Google or search ChatGPT. There will probably be a reference to OpenCV. So everything that you can do with other libraries, OpenCV can do much faster. There are some caveats. The first one is, as I said, it's based on C. So it won't be as easy to use as SkyImage. So when you want to have an angle, you should do something like a flag as we had in Pillow. So like this, you should pass a flag to do some operations. So this makes it hard to do custom operations a little bit. You should write some sort of tricky functions, and most of the times what I do is use ChatGPT to write me those functions. But be careful about this. The other thing is that natively, when it opens the images, and I don't know what's the reason behind that, is rather than opening it as RGB, so the first channel R, then G, and then B, it opens it as BGR, sorry. So it reverses the order of channels. I think it's based on a C convention, but I'm not sure about that. So when you open an image, the first thing you have to do, you open an image with IMRead, and then you have to convert its color space from BGR to RGB. So these lines will be added to your codes. And then the rest would be like SkyImage. So you'll get an array, and that will be a NumPy array. So you can see the class is NumPy array, and you can show it using the Matplotlib library. So this is the image, the third image that we'll be working on. As I said, you have to, when you want to do resize, you can pass, you can call resize an image and then your size. One thing to be careful about is the difference between, so here, the width comes first. And this is very important. So when you want to do your transformations, be careful. Using OpenCV, width comes first. Using SkyImage, height comes first. So that's a little bit confusing. And you can see with SkyImage, with OpenCV, when you change you do some operations like resize, or we can see later rotating, the image range will not change. So that will be between 0 to 255. And that's a very plus side for this library. And then when you want to rotate your image, you should pass a rotate 90-degree flag. The flags are much more versatile than what is available for Pillow, but still, for example, you can't do a 23-degree rotation, which might happen as part of your data augmentation pipeline. For that, you have to have a affine matrix created. So don't worry about it. This function was written by ChatGPT. I admit that. So you can just rotate your image. You write this wrapper function to create your affine matrix, and then warp your image with that affine. So if you have an image here, you want to rotate that by 45 degrees, this is what you will get. Or here you can change it to 23 degrees and it will work also. Okay, now what if we want to convert our RGB images to grayscale? That's another thing. So here you can have this convert color function that we call, and then pass it the RGB to gray, which makes it grayscale, which is like what we did before with NumPy, and getting the uh, mean of the last channel. The next one, so you see here, the channel dimension has disappeared. And I think one of the last things that we do here is binarizing an image. So as I said, binarizing means making the image either zeros and one. So it's this library, OpenCV, you can automatically create a threshold and binarize an image based on that. So these are two. This is Otsu, which is some sort of adaptive thresholding method. You just pass in the flag, and you can say this is the range. And when you run this, you see your image now is binarized. So all these pixels are either 0 or 1. Or I think here 0 or 255. And for saving, you can just call I'm right, give it the file name, and then the binary image, which is the array that you had here. Note that OpenCV and SkyImage both work with arrays. So that's a very good thing. So you can use both when you have an image converted to an array. Based on your need, you can use either of those libraries and they will work. Just be careful about the difference between where, in which one height goes first, in which one width goes first. So if you mind these differences, then you'll have a very easy time switching between the two libraries and using compatibilities from both of them. So here is the binary image that we saved, and this is this. Okay, and finally, working with videos. So as most of you know, or all of you know probably, videos are just to show a video, you're essentially showing images in sequence with high speed. So that's the speed is called frame per second. So that's the way that we measure the speed. And then the images are just static images. So when you want to manipulate a video, you can just get the individual frames or individual images of that video, do whatever you like with that, or for example, resize that, make it smaller, and then open that or write that to a new video file. That's essentially what's happening here. So with video capture, which is a method, a function, I guess, for from OpenCV, you create a video, it's a method. You create a capture, and I also created a raw capture, which I want to save my images to. And this is the size of that capture. So that's 100 by 100. I want to change this video that I have to 100 by 100. I read this frame by frame. So this is just a check from OpenCV. So if it's not true, you have to get out because it means that the video was finished. And then for each frame, I get the frame, I resize that by OpenCV to 100 by 100, and then write that to new capture. And here is the frame rate, or essentially the speed. And if I run this, I should get a new video here. So let's first see what our original video looked like. It's downloading. Oh, So this is also a video from Stable Diffusion. So these are all sequential images just stacked on top of each other and passing with a, I think, frame rate is 15 or something, like maybe less, I don't know. So this is the image created by the prompt blueberry pasta, I guess. And then as you move, we're changing to strawberry pasta. So what we did in this video, we are trying, in this code block, we're trying to make this smaller video. And I don't know if I can open this new one. Okay, now you see it's much smaller and different. You see the resolution is very pixelated. So at least we're at the right place. So this is how you work videos. You open them, you read them frame by frame, and do all the manipulations that you like on that specific frame, and then save that. This is a very good thing. There are other libraries out there like Image.io, which I usually work with. Uh, it only facilitates the reading part. It will give you a NumPy array, and then you have to play with that yourself, change the NumPy array however you like, and then write that to a new file. And for manipulating that frame, I usually use the OpenCV. So for example, I have a transition video like this. Let's say, now I want to have a progress bar that says going from blueberry to strawberry. And then I want this progress bar added to each frame of this video. So so the whole video has a bar down at the bottom that progresses from 0 to 1, something like that. Then I should open this frame by frame, use OpenCV to add rectangles, and then fill that rectangle by a certain amount to have this final progress bar at the bottom. So that's how you manipulate videos or play with them. Yes. And now finally, the final challenge. So as we said, just before going to that, any questions? Sorry. No. So making an image binary like this will cause all the details to be lost. But suppose that you have a mask here. So you are training a segmentation model and you want to have this segment here. So you can use binarizing as a first step to have this mask and then manually remove them. Or when you have this binary mask, there are some mask operations like closing, opening, erosion, dilation, etc., that you can apply on this mask to get rid of the noise that you're looking for. But binarizing does not remove the mask, it does not remove the noise by itself. So there are some ways. One thing that you can use is, so depending on what you mean by noise, for example, sometimes noise is very useful. So when we are doing augmentations, we add noise to our images. So our model is not sensitized on that noise that you're talking about. But maybe if you are, for example, you have some image noises that you want to really get rid of, maybe you can do blurring a little bit. That will get a lot of pixel noises that you see there. So one way to get rid of that is by blurring. But as I said, it depends on what noise you're talking about. But noise is not a bad thing. Just have that in mind, because when you train your models, you don't want your deep learning model to fit on those, to find those specific noises that help it overfit. Okay, and now finally, this last challenge. Here, as I said, we have 14 images in this samples folder. And we can, let's say, that'll be image 1 to image 10. I want you to write a function that gets the image path, which is essentially these, and an image size, which is an integer. So for example, I will give you 256 by 256. And then I want you to do these things. First, I want to read that image, read the image that's in this path with whatever library that you feel comfortable with. Pillow, Sky Image, OpenCV, because personally, I don't think it makes much difference. When you want to start a project, you just have to plug in everything together in a way that your code works, and then you can work on making it optimized and fast and remove the redundancies. So for now, I would say use whatever library that you feel more comfortable with. Open the image, convert it to 3 channels. Some of them have 4 channels, some of them have 0 channels, some of them have, I think, 1 channels. So you have to consider these edge cases. Then I want you to resize the image in a way that aspect ratio is not changed. And when I give you this image size of, let's say, 256, it means that the largest dimension should become 256. And for example, in this very, let's say in this image, yes. So if I give you 256, it means that this one should be 128. And then, so this would be a rectangle. I don't want the aspect ratio to change. And then at the third, I think, fourth place, I want you to pad the extra space around it and make it so that the image is the center of the larger image. So for example, in that case, I want you to add padding to the top and bottom. The top would be 256, 64, and the bottom should be 64 also. And then finally, save the image as a PNG in this new folder. So the folder is called /new image, new sample. So new samples is here. One question, Farhad and Eugene, can we extend the class for 5 or 6 minutes?
Yes, absolutely.
Yep.
Okay, perfect. Sorry about that. So you'll have 5 minutes, and then after that, I'll try to write this code myself in this time, and then we can discuss that, go over that. And there's also a sanity check cell after that. So if you want to see if your code is running or not, you can run this cell. And if you get no errors, and at the end you see all images are correct, it means that your code is right. At the meantime, I'll try to code this one and also find the bug at the previous cell. Okay. So, can you guys send me your code in the chat if you've written that? Otherwise, we can go through my example. Okay, so let's first share your, so what was your problem? You can write that in chat. Oh, sorry, it's here. Okay, so let's share my version first. Sorry, I have a problem sharing my. Okay, so I don't know what the problem is here. Yes, you can. Can see it, but I can share. Okay. Okay, so let's first go through the bug that we had previously, and thanks to Farhad for pointing that out. So that was a very simple bug, unfortunately, and it's very easy to miss. So here you have to have your D type. So you have to convert your image either here when you create the larger image or after you get the padded one, have the D type as uint. So if this is not uint or this is not integer, then you'll get an error when Matplotlib is trying to show that. But if you open that up in your browser or in any other image or in your, let's say, computer, then there will be no issues. So the problem is,
Sorry.
Yeah, I think
Oh, there we go.
I
It's
had
back.
the screen black, but now it's correct. Perfect. Yeah. Perhaps
oh,
the Zoom thing. Yeah. Thank you.
okay. So here, just be careful. So this is the thing that I added, and now it works perfectly. And so be careful about the data types again. And now to the code. So I see some people sending something in the chat. Okay, I just put this up code real quick. So hope it works. I don't know. Okay, so this is the code. So let's make it a little bit bigger. Close this. Okay, so it's a little bit longer than 7 lines. So first, you have to read the image I use the Sky image as my go-to library. So be careful with that. If you want to work with that, be careful to change the data types, which I think here I forgot. So first I read the image, then I take care of the number of channels. So if the image has 2 channels, two dimensions, which is height and width, which means no channel dimension. I expand the dimensions using NumPy. So by expanding the dimension means adding a dummy dimension at the end, and I at one place. So when I say axis equals 2, which means add a dummy dimension at the end. So now the image, if it's 2 channels, then it will be sorry, if it's only height and width without any channel dimension. Now after this part, it will be height, width, and 1. And if it's 4 channels, what I do is take the first 3 channels, as we said previously. And if it's only 1 channel, which is something, some images might have 1 channels, and some images might have something like this. So when they have no channels, we convert it to 1 channel. We concatenate the image at the last axis, which creates a 3-channel image. So this is the part that I take care of the RGB. Then I resize the image. How? So this is a bit tricky. So let's go through it part by part. So I first change the 2 dimensions, which is width and height, to NumPy array. And then I divide it to the maximum of NumPy array divided by image shape. So what it means is that here, the maximum of this one is, let's say, 1000. So we had an image of 500 by 1000. The maximum would be 1000 divided by image size, which means it's let's say 256. Then it means that this image has to become 4 times smaller. So essentially this part is this scale. And then if you divide everything by the scale, then you get the new dimensions. So this is how the new dimensions come from. Oh, I have to remove this, sorry. This is necessary. When I do a resize, then I add the new dimensions. I don't need this one. When I do the resize, I give it the image and the new dimensions, which is this one. When I want to pad, I want all my images to be np.0, so I create a 0. And based on what Farhad said, we change the d type to np.uint8. And then we put the larger image, which is this part, equals to our image. And now let's go through this. The first one is we get the image size. So rather than saying I want get the size from the larger image, we know its image size. So I say here, it's, for example, 256 by 256. So this is 256 minus the image after resize, shape divided by 2. So this means that half of the difference should be on the left. The other one is now add this and then add the image size to the beginning. So for example, if the image is 250, I will go 250 to the left, and then the rest would be zeros. This is, I know it's a little bit complicated, but if you don't do it like this, so if you do it like what we did previously, so we say image size minus image divided by 2, and then add the half to the right, so go minus this number. The problem will be if the pixels, the number is odd, then you lose 1 row of pixels or 1 column of pixels. This is not very, I think, critical in most of the tasks, but it might cause some issues. So you will lose 1 row or 1 column of your pixels. So this is a better way to do that. And then you have the channels to 3. And at the end, what I do is I get the image path, copied it from below, replace the samples with the new sample folder, have this new path replace JPEG to PNG, and then save the image with image.io. I will also, so let's do this. I will create a copy of this folder with this notebook with all the field examples and then put that in the repo. So if you want to use that later, you have all the codes there attached to it. So sorry it took 20 minutes longer. If you have any questions, I'm open to them. Otherwise, have a good rest of your day. And thank you, Farhad and Eugene, for the invite.
Thank you so much. That was a great presentation. I really enjoyed it. And I think our audience learned a lot. These concepts perhaps is new for many of our students and very essential for the future lectures, because we have many tasks, many applications working on different imaging and visual data.
Yeah, thank you so much, Vardia. I think this was a really, really interactive session. Everyone benefited a lot, I think. And if you can push the newer version with the filled code for the Google Colab to the GitHub now, or now that the session is over, we can share the new version with a completed code with our participants as well.
Yep, of course, I'll do that, and I'll update you when I do that, because I'm using my computer, so I have to go
Perfect.
home and push it from there. Yeah,
Perfect. Awesome.
Perfect. Thank you so much.
Yeah.
of course. Thank you.
Thanks again, and have a great day, everyone.
Thank you.
Yeah, we'll see you
Bye, everyone.
tomorrow for deep learning fundamentals. The first time we'll talk about deep learning.
Perfect.
Great.
Thank you.
You everyone. Thank you again, Bardia.